It's kind of amazing when you think about it. So many things we just take for granted in programming today.
Like what specifically?
Well, compilers, for instance. The idea of code that looks like English. Even the word debugging.
Ah, right.
Yeah,
It all seems to trace back in some fundamental way to one person.
exactly. And that's who we're diving into today. Grace Hopper, an American computer scientist, mathematician, and a Navy Rear Admiral, no less.
Quite the combination. And her legacy is, well, it's foundational, like you said.
Yeah.
So today we're looking at the sources you pulled together on her.
That's the plan. Our mission really for this deep dive is to get past just the list of achievements and really grasp the key insights from her life and work.
How her vision shaped computing as,
Mhm.
as you listening experience it today.
Precisely. And uncover some, frankly, fascinating stories about her journey along the way.
And we'll be using her Wikipedia page mainly, which is pretty comprehensive, plus some other texts that really dig into her major contributions and her lasting impact.
Okay, let's dive in. Born Grace Brewster Murray, New York City, December 9th, 1906.
And right from the start, there was this drive to figure things out.
Oh yeah, that story about the alarm clocks.
7 of them.
At age 7, she took apart 7 alarm clocks just to see how they ticked. I mean, talk about curiosity, something I think a lot of us can relate to.
Absolutely. And that wasn't just a childhood thing. It stuck with her. That need to understand the why behind things.
And not just understand, but question, right? Like keeping that clock that ran backward.
That's such a great symbol for her attitude.
And her quote about it is perfect. Humans are allergic to change. They love to say, we've always done it this way. I try to fight that.
That sums it up, doesn't it? That constant push against inertia, it really fueled her innovations.
Definitely. And she had the academic chops to back it up. Vassar for math and physics in 28.
Then Yale for her master's in 1930, and her PhD, also
Wow.
in math, in 34.
Her dissertation title was New Types of Irreducibility Criteria. Sounds intense.
Pretty deep mathematics, but it shows that foundation. And it's worth noting, she was one of the very first women in the U.S. to get a doctorate in math.
Incredible for that time. And just briefly on her personal life, she married Vincent Foster Hopper in 1930.
They divorced in 45, but she kept Hopper as her professional name.
Right. Okay, so let's move into her professional life. World War II was a huge catalyst, wasn't it?
Absolutely. Though getting into the Navy wasn't straightforward, she tried early on.
And got rejected, which seems unbelievable now.
Yeah, they said she was too old. She was 34. Her weight-to-height ratio was off. And even that, her job teaching math, was too important for the war effort.
Wow. But she didn't give up.
No, she kept pushing. Got an exemption for being underweight and joined the Navy Reserve, the Waves, in 1943.
Waves, women accepted for volunteer emergency service.
That's the one. And that led her to Harvard, to the Bureau of Ships Computation Project.
Working on the Mark VIII computer under Howard Aiken.
Exactly. Programming this massive pioneering machine.
And she wasn't just coding. She co-authored 3 papers on the Mark I-2, showing that deeper understanding.
Right. But then, after the war, she tried to transfer to the regular Navy.
And got turned down again, this time for being too old at 38.
The irony, considering her later career. But her path in computing was really just starting. 1949, she joins Eckert-Mauchly Computer Corporation,
As a senior mathematician. And this is where she gets involved with the UNIVAC I.
which becomes the first big, commercially available electronic computer around 1951. She then becomes UNIVAC's Director of Automatic Programming Development for Remington Rand.
Okay, so automatic programming. This is where her big vision really comes into play, right? Making it easier.
Yes, that famous quote captures it perfectly. It's much easier for most people to write an English statement than it is to use symbols.
So she basically thought, why can't we just tell the computer what to do in English, more or less, and have it do the translation work?
Exactly. A radical idea then. Most thought computers only understood raw machine code.
But she went ahead and did it. By 1952, she had the first compiler, the AO0 system.
Right. It translated symbolic math code into machine code.
Think about what that meant. Before that, programming was this incredibly tedious, error-prone process, direct machine instructions.
Ones and zeros, essentially.
Yeah.
Her compiler automated that translation.
Making programming faster, way more reliable,
More accessible to people who weren't electrical engineers.
and making the code itself reusable, scalable. It's really the bedrock of modern software development in many ways.
And what's amazing is the pushback she got initially. People were skeptical that a computer could program itself, in effect.
But she had a working compiler. And she just kept pushing for it.
And it paid off. In 1954, they made her the company's first director of automatic programming. That's a
Oh.
pretty clear sign of her impact.
And under her, they developed languages like Mathematic and Flowmatic, early compiler-based languages.
Which leads us straight to COBOL.
Ah, COBOL. Still running systems today, surprisingly.
It really is. In 1959, she was part of the Codicil Group Conference on Data Systems Languages.
Right, the consortium to create a common language for business.
And COBOL drew heavily on Hopper's Flowmatic, plus some ideas from IBM's Common Tran. The key was that English-like syntax.
Like that example. If Balansario then display overdraft, you can actually read it and understand what it's supposed to do.
Revolutionary for business applications back then.
Yeah.
And it just took off, became the standard for banking, government, insurance.
So much of the world's infrastructure ended up running on it, and much still does.
Speaks volumes about the design. And she stayed involved, directing the Navy's programming languages group from 67 to 77, focusing on standardizing COBOL.
Beyond just languages, though, she was thinking bigger picture, too, wasn't she? About systems.
Definitely. Even in the 70s, she was talking about decentralized computer networks.
Like interconnected systems sharing data. That's pretty forward-thinking for the 70s.
They vary. And she was huge on standards. Developed testing standards for computers and languages like Fortran and COBOL for the Navy.
Tests that later got picked up by the National Bureau of Standards, now NIST.
Right. So that focus on interoperability, making sure different systems could work together.
You can see the seeds of things like cloud computing, containerization, that kind of thinking, making systems work as a whole.
Exactly. Not just isolated programs, but an ecosystem.
Okay, let's jump back to her Navy career for a second. She retired from the reserve as a commander in '66, but that wasn't the end.
Not by a long shot. They kept calling her back to active duty. Retired again in 71, called back again in 72.
Then promoted to captain in '73.
And then, the really big one. In 1983, President Reagan promotes her to Commodore.
Which later became Rear Admiral, lower half.
And she finally retired for good in 1986.
At age 79, the oldest serving member on active duty at the time.
Incredible. And she got the Defense Distinguished Service Medal, a very high honor.
So her Navy service ran in parallel with all this massive impact on computing.
A remarkable dual career.
And even after that final Navy retirement, she wasn't done. She joined Digital Equipment Corporation, DEC, as a senior consultant.
And stayed there until she passed away. But she wasn't just, sitting in an office.
No, she became this sort of ambassador, right? Traveling, lecturing.
Yeah, a goodwill ambassador for DEC and for computing in general. Talking about the early days. Her vision for making tech accessible.
And apparently she always wore her Navy uniform for these talks, even though she was retired.
That's right. A powerful symbol of her identity and service.
And she was really passionate about mentoring young people, wasn't she?
Immensely. There's that great quote, "The most important thing I've accomplished, other than building the compiler, is training young people."
Yeah, they come to me. Do you think we can do this? I say try it, and I back them up.
That says so much about her approach.
Yeah.
Encouragement, giving people the chance to try things, maybe fail, but learn.
Fostering that next generation. Okay, we have to talk about the bug story.
Oh, the moth. Yes. Classic.
So what actually happened there?
Well, back in 1947, working on the Harvard Mark II, the machine wasn't working right. And they tracked down the problem to a relay.
Yeah.
And stuck in the relay. An actual moth.
A literal bug.
A literal bug causing the problem. So they carefully took it out, taped it into the logbook.
I've seen pictures of that logbook entry.
Yeah, and wrote, "First actual case of bug being found."
Yeah.
Now, the term bug for a glitch existed before.
But this story just cemented it, right? Especially in computing.
Exactly. Hopper told the story often, and it just stuck. A perfect, tangible origin for debugging.
It's brilliant. And she had a real knack for making abstract stuff concrete, didn't she? Like the nanoseconds.
Oh, the nanosecond wires.
Yeah.
Yes. She wanted to explain why there was a delay in satellite communication.
Yeah.
So she'd hand out these pieces of wire.
Just under a foot long.
Exactly, 11.8 inches.
Yeah.
And she'd say, this is how far light travels in 1 nanosecond.
Wow. So it gives you a physical sense of this incredibly short time.
Precisely. Made things like signal speed and computer speed tangible. Not just abstract numbers. Later, she used pepper grains for picoseconds.
That's just fantastic teaching. I also saw that quote describing her as all Navy on the outside, but a pirate dying to be released inside.
That captures it well, I think, that mix of discipline from her Navy background, but also this rebellious challenge the system spirit.
She worked within the system but wasn't afraid to shake it up.
Absolutely. Sadly, she passed away on New Year's Day, 1992, age 85.
And was buried at Arlington National Cemetery with full military honors. A fitting tribute.
Indeed. But her legacy? Well, it's everywhere. The number of honors and things named after her is just staggering.
It really is. Let's see. Defense Distinguished Service Medal, Legion of Merit, National Medal of Technology.
Posthumous Presidential Medal of Freedom in 2016.
The Grace Murray Hopper Award for Young Computer Professionals started way back in 71.
40 honorary degrees.
40. That's unbelievable. And then the actual things named after her.
The USS Hopper destroyer. The Cray Hopper supercomputer. NVIDIA's Hopper GPUs.
Grace Hopper College at Yale. Hopper Hall at the Naval Academy. The Grace Hopper Academy Coding School. A bridge. A minor planet?
Google's Grace Hopper undersea cable, and of course the huge Grace Hopper celebration of Women in Computing Conference.
It's an incredible list, even showing up in the Matplotlib Python library. Her influence is just woven into the fabric of tech.
And still being recognized. Like just this year, 2024, the NSA released a talk she gave in '82, and the IE dedicated a milestone for her A0 compiler work.
It keeps going, and it really all comes back to that core philosophy, doesn't it? Challenging. We've always done it this way.
That was her mantra. That and our absolute focus on making technology work for people.
Yeah.
Making it more accessible, more user-friendly.
She saw the power, but knew it had to be usable.
Exactly.
So wrapping this up, Grace Hopper, truly a visionary, not just for the technical breakthrough as the first compiler, paving the way for COBOL.
Which were monumental on their own.
Right. But she also fundamentally changed how we even think about computers and how we interact with them.
Her curiosity, her persistence, especially when people doubted her, and that core belief in human-readable technology, it's left such a huge mark.
You can really draw a direct line from her work to so many tools and concepts you use every single day, probably without even realizing it.
Her innovative spirit just echoes through modern technology.
So maybe a final thought for you listening. Think about your own world, your work, your interests. How many times do you bump up against that "we've always done it this way" mindset?
What established rules or ways of thinking might actually be holding back the next leap forward?
Maybe there are some assumptions worth questioning, some rules worth bending, or even breaking Hopper style to unlock something new?